All right, when we were together last, we had this fun little project, and we talked about flattening the curve, and I kind of sketched the curves over on my board. Pretend like where you see the y-axis, pretend it's not there, right? So we had that conversation about the two curves and that whole idea. So what we begin understanding is when we're looking at how quickly something is spreading at any given time or how much something is changing at any given time, what you learned about comparing these two curves was the amount of the x-axis. How big of a bite of the x-axis did you take? And this was all about looking at different sized bites of that x-axis. So when you walked your way through this project, you ended up looking at some data, and this data ends up being the important kind of stuff where it says, you know, if you look at how quickly the virus spreads in this during this time, you can begin to look at when there was a change in just 5 days, there was 184 cases, that averages to 37-ish cases per day. When you take each day, each chunk, 5 days at a time, you can see how that average rate of change of growth of the cases dramatically changes. At the very beginning of the project, when we looked at just all over 30 days, didn't it work out to be like 5,000 cases a day? Wasn't that about it? Wasn't it like 5,600 cases a day? Who's got a head for numbers? Who remembers? You don't have your pockets, you turn them into me. Wasn't it about 5,600 cases? Yeah. So that first couple days, when it's only 36 cases a day, if you're telling me it's 5,000, we're not even in the same ballpark. On that last day, if you tell me we're growing at a rate of 5,000 cases per day, again, we're not even in the same ballpark, because those last 9 days, that worked out to be 15,000 per day. So I want you to start thinking of this as how big of a bite of the x-axis are you going to take? Even if you just look at that first week, 0 to 7 days, 56 cases a day, 0 to 5 days, 37 cases a day, 0 to 3 days, 23 cases a day, but really if you just look at 1 day, it was 23 cases. So the numbers are all over the place. So then we had you do your homework, and on the homework, you're introduced to this word that we didn't really talk about. I just told you, do your homework. But you might have had that at the end of pre-calculus. Do you remember talking about the derivative at the end of pre-calc? So what the derivative is, and you can take this homework sheet out because you have this for homework. So this is your homework. So you spent the last couple days thinking about this and reading about this and being curious about this, being academically into it, being like, I'm so curious, because we're going to introduce to you two big words. One is instantaneous rate of change, and one is the average rate of change. Hey, I want you to look at something. If I'm talking about the rate of change between these two curves, and I'm looking at this, and I'm looking at this change, when you're comparing your green and your pink curve, it will be about the same, right? If I'm taking a look at this rate of change between this bigger bite of the x-axis, I got a big difference between those two conversations, between those two separate curves. somebody came and asked me a question about the homework. They're like, I don't understand the two curves at the same time. And I'm like, well, they're two completely separate scenarios. Does that make sense to you? Like, the pink curve was what everybody, scientist-wise, they were afraid we were heading towards. What am I missing on my graph here that would benefit our conversation? Yeah, that healthcare system. And wasn't that like, we'll put that right about here? You okay with that constant? Yeah, that line there said if we go above that line, we're out of ventilators, we're out of ICU beds, we're out of healthcare professionals, we're out of ambulances, we're out of PPE. You know what PPE is? That personal protective, right? We're out of gloves and masks and gowns and like we're out. So when we talked about flattening the curve, we needed this average rate of change to look different. The red curve was what we were afraid was going to happen. The green curve was what we were hoping we could make it. We were living in this zone here. Does that make sense to you now with the two curves? Does that clarify something? So the important thing is, when we're looking at how many cases per day can we handle, our chunk of the x-axis that we take significantly changes our chunk of the y-axis that we're analyzing, output per input. We're okay with that? So when we talk about our average rate of change, our average rate of change, y'all, that's the same as the slope. So when we talk about y2 minus y1 compared to x2 minus x1, if we had a situation that was linear, we could talk about that average rate of change is the same throughout. So this becomes a fine equation to use at any given time because the line is straight. So that slope, that average rate of change, it's good for all parts of the line. That was algebra 1. We're good with that, right? Here's the problem. Average rate of change, not really doing it for me with the curve. So what we need to do is we need to think about, can I take a smaller bit? Can I take a smaller bite of x? Instead of having this be the x's that I look at, can I maybe make my bite of my x smaller? And if I get smaller and smaller and smaller and smaller and tighter, am I going to increase my accuracy? What did we just study last unit where our fingers were doing this? And we were looking at what the behavior of a function was from both sides. So we begin to be like, okay, how small of a piece can you bite? I can bite a piece this small. Oh, smaller? I can bite a piece this small. Oh, wait, smaller? I can bite a piece this small or this small. So what I want to end up doing is I want to know exactly at this point what the average rate of change is. And I want that space between the two input values I'm looking at as small as I can possibly get. Because when I get down to the limit, or this exact thing, I change from being my average rate of change to my instantaneous rate of change. I want to know what the rate of change is at this instant. My instantaneous rate of change there. I want to know what's happening there. So we call that the derivative. The derivative is going to be the instantaneous rate of change between two quantities. We estimated the derivative of that COVID-19 data for curve A. And when we talk about t equaling 1, wasn't that one day after for the curve? Wasn't each day after? Like March 1st was day 0. Remember that? Adrian, when we talked about 30 days being 19, right? So when we talk about curve A for that, as soon as we talk about T1, Your answer for this should match this. Read what I have written, read what you have written, talk to your partner, and see how accurate you are with your homework. Are you mark and set, go? Billy got the paper? Reader?
Yeah.
Everybody get the paper? Do you need one? Nope, you got it. Okay, take it out. Get some pen out. Do some work. Do some thinking.
Sorry. There's a complete so I said the rest of my I already got it. I was I could like basically like scan this and then like right on top of the colors and stuff. It's awesome.
Is here now? Is here now?
Are you okay with
If I try to like
Yeah,
having more fun than us, I'm
100%.
gonna be super practice.
Yeah, okay. Well, like as long as I'm not sure.
Yeah, just stay on task. You do you. Thanks for asking her.
Yeah, I just want to like take out the iPad, you know.
Yeah, no, I get it. All right, so if the derivative is the instantaneous rate of change between two quantities, it's obvious that curve A is changing more. So that derivative is going to be a greater value because we have a steeper incline and a higher change happening here. All right, so there we have the table that gives us the temperature of Herndon T hours after midnight during January. Use this information to estimate the derivative at 3 a.m. So here's the thing. Here's 3 a.m. and its temperature is 26.7. So what the interesting thing is, it says use this information to estimate the derivative. Explain why you chose the interval that you did. So here, why did I pick 3.25 instead of 2.5 as my x chunk? Think about the bind of the x-axis. Why did I go between 3 and 3 1/4 instead of 2 1/2 and 3? How come?
It's the smallest interval.
Yeah, thank you, Catherine. It's the smallest interval. So I'm not going to look at the time closest to midnight. That's where it's the furthest from what I want. I'll get the greatest average, but I want to know the instantaneous or the derivative, the smallest rate of change. So I can see that it's changing 0.4 of a degree at an hour. On general principle, we want to make sure that we are using the smallest interval possible. All right. Daniel uses the following rate of change to estimate the derivative of the function when x is equal to 8. So take a look at what you see here versus what I have over on the board. And you can see that my slope formula ends up growing up. It's like it needs to put its big boy pants on, right? So here's my slope formula. And instead of y2 minus y1, our only change is the fact that we're going to say it's going to be f of x2 minus f of x1 over x2 minus x1. That average rate of change, when we get to calculus, we have to make it a little fancier, don't you think? That means the output of the function given that input. So when I put f of 9 minus f of 8, that's my output, that's my y is 9 minus 8. So Kathy uses a different rate of change. Notice instead of having an interval of 1, like Daniel, what is Kathy's interval? What is it? Yeah, it's 1/100. So Kathy is looking at a much closer, a smaller bite of the x-axis, if you might describe it like that. So Kathy and Daniel are not going to get the same answer. And I would venture to say Kathy's is going to be more accurate. Because if she's looking for an instantaneous rate of change at that moment, the closer she is, the smaller her bite of the x-axis, the more accurate she'll be. Turn to your new partners and say, are you getting this?
Whoa, hang on a second. Oh.
All right, you ready for the back? All right, so B of T represents the buffalo population in the United States, where T is measured in years since 1880. So this is just simple going back to function notation. What does B of 90 represent? That's the number of buffalo after 90 years. So this 90 right here, that's my input. I put 90 into my function. You're like, what function? I'm like, I don't care. Nobody told us the function. So we don't know what the function is. I just know if I put 90 in, 90 years after 1880, which would be 1970. Did I see that? Was it the, I don't know if it was whatever social media platform it was on. It was all the buffalo running down the road in Yellowstone.
Oh, I saw that.
Did you see that? Isn't that crazy? Like, amazing. Wasn't that like yesterday?
Yeah.
Yeah, it's not like. So it's the number of buffalo 90 years after. So our output is the number of buffalo. Our input is those 90 years. So when we talk about what does this represent, that is going to be our average rate of change. I have that big bite of the x-axis. I'm looking at the change over 50 years. The average rate of change of the number of buffalo from 1880 to 1930. That's our average rate of change. Suddenly they change our input value, and I only have, what is the difference between 32 and 31.999? First decimal place is 1/10. The second decimal place is 1/100. What is that third decimal place? So we're talking about only 1/1000th of an inch past what I care about at 32. Hey, since that change, that bite of the x-axis is so incredibly tiny, we're going to go ahead and change the name of what we're finding. When we had a big bite, 50 degrees in between or 50 years in between, we can call that an average because it's over a long period of time. When that bite is super small, we're going to change what we talked about, where I say, you know what, that's kind of a change in an instant, because even though I'm not right there, I can't measure it right at that minute, but I can look at it super close and take a look at that. With your partners, what is the difference between average and instantaneous rate of change? Turn and talk and explain it. Go. Are we good? All right, Brady gives me a thumbs up. I love it. Okay, in a country, I don't know which one. I'm kind of curious. The number of deaths in a year can be modeled by the function D, where D of T is the number of deaths and T is the number of years since 1950, and I'm only giving myself 50 years of a range. So D of 40 means 40 is my input. I'm looking for the number of deaths. My output after 40 years. So when I add that 40 onto 1950, that's going to give me 1990. The number of deaths in the year. When we talk about the average number of deaths, we have a bigger chunk of that x-axis. In fact, how big is our chunk for this equation? How big of a range between my input values am I talking about? How big? Come on, you use that math in here. How big? 10, thank you. The average number of deaths between 1960 and 1970. If we want to know this, it becomes a new notation. That D really has nothing to do with deaths. Don't think we're carrying that through the unit. What ends up happening is we use in calculus and mathematics the delta symbol, or the change in y compared to the change in x. And what happens, this delta becomes such a small value that we end up just calling it dy dx. So if you're curious, are we supposed to know the difference between average and instantaneous rate of change? That D as a letter doesn't mean deaths. It was a bad example to talk about deaths when we introduced dy dx. But that D is different from our triangle because we want everybody to know that's that itty bitty 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 difference that we can use the term instantaneous instead of average in our conversations. All right. For number 6, you had to use the table to find the average rate of change on the given interval. So from 3 to 13, notice those changing x's go down in my denominator. So then I look at 10 minus 4. 10 minus 4 gives me an output of 6. 3 minus 13 gives me an output of 10. Oh, darn it. Not so round. So it's going to be 3 tenths. When we talk about the interval from 0 to 12, that's we end up with 5 minus negative 2, so we'll give ourselves a positive 7 compared to 12 here. God bless you. For letter C, negative 7 to negative, or from 3 to 4, gives us an interval of a change in 1. And then, of course, this is negative 11. So 2 minutes versus whatever that might represent. Everybody good? Yeah, Catherine.
For number 6, letter B, why couldn't you do negative 7 minus 4 over 4 minus 3?
I don't know. Let's go back and look at it. So the average rate of change on the interval. So I did 12 minus 0, and then 5 minus negative 2. What was your question? Why didn't I pick?
Why couldn't you do like the for T, the 3 and the 4, and for like, I did negative 7 minus 4 over 4 minus 3.
So
in between.
Right. So because this talks about the average rate of change on that whole interval, I want to include that whole interval.
Okay.
I want to know where it stops and starts. And because it's average, I'm okay with a bigger bite of the x-axis, and I want to represent that whole time. If I cut it and use an input value of 3 or 4, I'm not necessarily including my whole interval.
Okay, thank you.
That's a great question. All right. So here's what I want you to do. I want you to turn to your group mates. I want you to say, I'm glad I did the homework because, I wish I had done the homework because, regardless, from this homework I learned. And you have to say go. All right, Veronica looks at her curve and she goes, so derivatives are just the instantaneous rate of change? Yes. But we're going to take a long way to get there today. Are you ready? I can represent the derivative graphically. Is it going to work for me today? I can represent the derivative graphically as the slope of the tangent line. Hey, that's what ends up happening when we're talking about our derivatives. It's the slope of the tangent line. So the derivative is our instantaneous rate of change. And when we can look at that instantaneous rate of change, we get information about how the two quantities are changing together at any given instant. So last class we went back and looked at that data for the CDC and COVID-19, and we tried to look at how the virus was spreading. And this graph is one that was the same as what was in your packet. The difference between 0 to 7 days, 0 to 5 days, 0 to 3 days, or 0 to 1 day. And we can see how those numbers of cases end up changing. So what's pretty cool about this is we can look at this using a graph. Hey, Doc, you change seats. Come on, join these guys over here. He even knows to go to the basket. Nice job, Doc. You can also put up the Smarties with being so smart. He's excited. This is the coolest graph. Is it going to open? It's probably opening on my other computer. I really want you to play with this graph, and I'm going to put this link on Schoology so you can play with it because you're going to love it. Okay, so this graph does a pretty good job of looking at it, and I want you to think about what we said. The derivative is the slope of the tangent line, right? So if you look at this function here, this quadratic, this upside down quadratic, here's this function here, negative 1/2 x squared plus 6. So we have a y-intercept of 6, negative, so it's reflection, it's a quadratic that's down like a frown. Everyone okay with that? So what we're going to talk about with the derivative is, do you see how h is the distance between my x values? Do you see that little h that's there? So the h here is just going to be x2 minus x1. So I give you that subtraction problem. We solve it here for ourselves. What I do is this y value that I'm playing with here is this is the input, or that's the output of x plus h. This is the output of my original x. So my original x is here in red. There he is. My output is f of x. My input is getting closer and closer and closer, where h is getting smaller. And you can see that as h gets smaller and smaller, what I really end up finding in that instantaneous rate of change is the slope of the tangent line. And it's kind of cool when you click on it and see the bigger h gets, really the more ridiculous our answer is, because it's the further from the truth. I know that the slope of this tangent line, when I approach that limit, is -3. I don't get an answer close to -3 at all in any other part of the curve. But the closer I get to having 0 being the difference, now I got to tell you something, we can't put 0 in as a difference. Hi, Maria. Grab it, hang it on the basket. I can't get 0 as the difference because, check it out, it's in my denominator, and that gives me 0 in the denominator, and that's breaking all the rules of mathematics. So what I have to do is actually start calculating the limit. I have to find as close as I can to h being a value of 0. I'm finding that limit as x gets closer and closer and closer to h. So every time we're thinking about this, I want you to think about this tangent line, this dotted line that's tangent to this exact moment. That's the slope. That's the rate of change at that given instant. We thought that graph was kind of cool. All right. If the graph represents the COVID curve from the last class, What do the following represent in context? Talk with your partners and see if you can fill in what we're talking about with that graph. You ready to lock in?
Oh, it's down here, right.
If the curve represents the COVID curve from the last class,
Texas.
what do the following represent? What were we measuring across our x-axis? Time. So we were talking about time, more specifically, wasn't it our days in March, right? So our days, and we'll go ahead and put March, because that's what we were, those first 30 days of March, right? Do you remember how you felt those first 30 days? Weren't they surreal? You're like, wait, what? We're not going back to school? Do you remember, wait, what? Wait, what? Like, do you remember how you felt? True story, you were a little excited.
Well, I was jealous of Loud and the kind of baby were.
Right?
I was like, how dare they?
Right?
And
Right?
then it was like 2 weeks and I was so nice.
What would you have thought then if you had heard that, what are we up to, over 700,000 deaths? Like, what would you have thought, right? That's crazy, right? So those first 30 days were an interesting no. Take them all.
Yeah.
Except I think I got one stowaway. Oops. Yeah.
I'll count them.
All right. What are we measuring? What's on our y-axis? Yeah, we're measuring COVID-19 cases. So what does that H represent? Was that you that said that? I can't tell because of the mask. Was that you? What did you say? Yeah, the interval. See, now we had to go back to my original screenshot because now Nadia doesn't have any friends to sit with. Hi. Go sit in that seat. And we're going to send Grace, pop over and be your friend. What does H represent? I heard it here. Yeah, the interval that we're talking about. What did I refer to it casually as? It's 296 although that's not casual. What do we refer to casually? I talked about it as our, yeah, that, how about that chunk of the x-axis, right? What are we looking at? So if we're talking about this, we can talk about it as our interval between the inputs, interval between our inputs. Maybe I want to talk about it as a chunk of the x-axis. Whatever you write there, make sure you understand it. And what does that delta y represent? Not yet. Not yet. Here it is here. What does it represent? Yeah, that's our change in our output. It's going to be our change in our output. That's our change in output. And when we put it together, when we talk about that slope, of our dotted line, that's our change in y compared to our change in x. We can talk about that is our slope. We can talk about that's our rate of change. And what we want to do is we want to make it so the average is approaching, got my S. Instantaneous. Instantaneous. We want to make it so that our average rate of change is approaching the instantaneous rate of change. And the way we're going to do that is we're going to make H approach 0. And instead of having a change in y compared to the change in x, we're going to have that become a little change in y compared to a little change in x. So when I go from the delta triangle to the D, that's your symbol. So we're not talking about a big chunk of the x-axis here. We're talking about just the tiniest bite. Sound okay? Say yes. Okay. So here's the notation for the derivative. y2 minus y1, change in x, change in y, dy dx. The derivative is our instantaneous rate of change. But when we want to look at that instantaneous rate of change, we need this change in x to be extremely small. And that's how we go from average to an instant. Okay. We go. All right. So when you look at these two graphs, what do you notice as the 2 points get closer and closer together? What connections can you make from our next class? So what I want you to do is take a look at the green, and you all have colored pencils at your desk. And you all have straight edges at your desk. Take that straight edge, please. There should be enough for everybody. If there's not, I'll get you more. And what I want you to do is I want you to balance that straight edge on the curve, and I want you to see this green line is what we call the tangent. And this tangent line, you'll remember from geometry, touches that curve at exactly one place. So what I want you to do is I want you to slide that ruler so that you're really looking at it just touching one place, and take a look and see if that feels like it matches to you. So for example, if I was taking my ruler here and I was trying to find my instantaneous rate of change, this is not going to do it for me. But what I want to do is slide it so it's touching it at exactly one place. You may have to tilt the ruler up or down, make it match, but it should hit that green line exactly. Get a colored pencil and draw it. And what we want you to see, that here, our red line represents our average rate of change. That is the change in y compared to the change in x. That's the change in y compared to the change in x over that bigger piece of the puzzle. Good. As h gets smaller and smaller and smaller, do you see how this red line approaches and gets closer and closer and closer to being coincident? Remember that word from algebra 1? Coincident with that red, with that green tangent line. That is because my x becomes so very small to the point that I wind up having a dy dx, which is where I get my instantaneous rate of change when I'm looking at that value there. Derivative is the instantaneous rate of change. Graphically, the derivative is the slope of the tangent line at any given point. And the thing is, we can't just take a tangent line because we can't take the slope, because if a tangent touches it at one point, I can't get a slope from one point. And that's where all of our Unit 2 limit conversations are going to come into play. All right. So here are lots of tangent lines at many different points. And is there a way I can calculate the overall derivative for the function? So I'm going to have a function, and there's an infinite number of x, y ordered pairs that sit on that line, and I can do the derivative at any one given point, but that function has a big shape, so I need a rule, I need an equation, I need a formula that I can calculate that derivative at any given point as soon as somebody gives it to me. Like, I can do it at an x value of 1, I I could do it in x value of 12. I could do it in x value of 563, but I want an equation that's open for any x or y value that somebody wants. And that's what we're going to start doing. We calculate the derivative by calculating the rate of change between 2 points that are infinitely close together. And because they're infinitely closer together, we're taking the limit as h, that space between them, gets tighter and tighter and tighter and tighter. Now what we need to do is take a look at what this means. And we need to identify each of the different parts of this formula. So let's remind ourselves that our h is equal, do you want to call it like the space? Do you want to call it the interval? What do you want to call it as far as the changes between the x's? What would make sense to you? The interval? H is equal to the interval between x2 and x1. So that h represents how far did I go. Notice when I simplify this, that x and that, those two x's, see how they cancel out? And that's where I get just h in my denominator of my formula. Does that make sense to you? So if it's x is here and x plus h is here, when I go to do the subtraction problem, x plus h minus x, I just get h is that distance. You okay with that? H is that distance between the two. F of x plus h minus f of x, that's just the difference between our outputs. That's just y2 minus y1. That's going to be our difference between our outputs. But this is the kicker here, that you can understand what happened to those x's. H just represents that distance. If you feel like you want to draw a sketch of the graph down here, and you want to talk about this here, and we have here our x1, and we have here our x2, then you can know that this here is h. That's our, okay? Yeah.
Is there a reason why it's called the tangent non-negative after each triangle?
So, the great question. So, tangent is a word that we first experienced in geometry, but when you know it in pre-calc and trig, it's sine over cosine. So that tangent line represents the ratio between your sine and your cosine. Think about how tangent is sine over cosine. Isn't that slope? Changing y over changing x. Did you ever wonder why tangent was sine over cosine? That's your line that is the slope. Isn't slope changing y over changing x? You see that connection?
But like it's not, does it have to do with the triangle though?
Yeah, so that triangle represents, that's, remember in slopes when you would do like rise over run? So think about your slope as you go rise over run. We have that triangle representing all those changes when I'm starting to look at the difference between my x's and the difference between my y's. It's interesting in mathematics how many times we see that triangle. Remember in distance in geometry when you use that for distance? Do you remember what I'm talking about with distance? So when you talked about distance on the coordinate planes here, you always had your x1, y1, and your x2, y2, and you talked about your change in your x's, because this point here was over x2, right? And this point here was up y1. So this here was always the absolute value of x2 2 minus x1. And this here was the absolute value of y2 minus y1. So that triangle has always been, and we want to find that distance. That's always been that same x2 minus y, or x1, y2 minus y1, and that's what gave us our value for the distance. If I wanted to find the slope of this, that's the same as my rise compared to my run. Change in y over change in x. That's that tangent line. And I can find that moment on that curve. Let's say I had a curve. That went like this. That tangent is going to be, that's that slope at exactly that moment. Does that make sense? Okay, next up. So what I want you to do is sketch the derivative of each graph for the given point. So here's some notations that I want to make sure you understand. When you see this little prime, I don't want that in blue. When you see that little prime there, that's the notation for the derivative. So f prime means that the derivative at an input of 2. So with your straight edge, look at an input of 2. Gives you that output there, yes? So what we want there is then for you to be able to draw a line that's tangent and touches that graph at exactly one spot. That tangent line is going to be, and play with your straight edge, have a spin. I have more straight edges if you need them. My geometry people steal them. You tell them down. Don't they do?
No. That's not.
So, isn't this to me, the copies are a little bit hard to read. This to me is 2. And this says -2. Do you see that? So then this is 2 and this is 4. Jaden, does that help?
Yes.
So, for what you just made, is that the only way that you can draw the line, or is there like many possibilities?
Super many. No. There's a way that we can get it other than drawing, but there's exactly one. Exactly one tangent line at that point. What's the matter? Simon has a very curious look on his face. I'm curious why he's so curious. Simon, why are you curious? Maybe this one will be a little bit easier. Maybe this one, Simon, will be a little bit easier for you to draw. If I want to know the derivative, remember, and add this to your notes, that this f prime that f prime is the notation for our derivative. When I look at 4.5, negative 1, 2, 3, 4.5, that's going to be this input. So when I come up and I look at where that is on the graph, are you okay with that right there? If I go to draw the slope, if I go to draw a tangent line, I want to make sure that I can make it so that it's only intersecting my graph one time. If it's intersecting twice, it's not a tangent, it's a secant. So is that one a little bit easier for you to draw? I'm putting my dot. This is my input. So here's my input. So that's where I'm putting my dot. If that's my input, I go up and I reach that on the graph. So that's my output, whatever it is. So then when I draw that slope of the tangent line, that's my instantaneous rate of change. Whatever the slope is of that line, that's how quickly that graph is changing at that exact moment. So please keep asking. Okay, here comes the calculus part. Ready? So this is the next problem. It's not related to the graph above. Find the change, the dy dx, of y minus, or y is equal to 7 minus 6x. What we need to then find algebraically is what happens as that h approaches 0. So what I need to do is I need to take the limit as x approaches 0 of this function. So what I need to do is I need to find f of x plus h minus f of x, and I need to put that over h. Now, if you plug in 0, go ahead, quick do it. Everybody roll your eyes and sigh at the same time. How come? Because right away, you see that you can't divide by 0. And if I put 0 in, oh, this is as h approaches 0. I'm sorry. Make sure that's h approaches 0. Because if I put 0 in for this h, I get f of x minus f of x, so what do I get? Then we have our indeterminate form. So we need to do a little bit of algebra. Are you ready? Are you ready? So what we're going to do first is take our function f of x, and we're going to say, okay, I have f of, and I have x plus h. So f of x is 7 minus 6 times, and I'm going to have x plus h, and then that's going to be minus your function f of x, which is 7 minus 6h. Here is my f of x. Here is my 7 minus 6, and instead of writing x, I'm writing x plus h. Are we okay with that? Yeah? Oh, and I forgot about my h. Hold on a minute. And I need to put my h here. And I don't need this f. There we go. Seven minus 6x is my original function. Is everybody okay with 7 minus 6x here going in for my original function? Do you see that? Okay. Here's 7 minus 6, but instead of it being x, it's x that's going to be h away from where my point is. So if we go back to where h is my, so if I draw this, remember how I had my 2 points? And I said that this represents my h, my distance between my x's. What I'm going to do is make that distance smaller and smaller and smaller and smaller. Let's go back to that fun graph that we had. As my h got closer and closer and closer and closer, here's my f plus h, here's my f of x, here's my h. As this gets closer and closer and closer and closer, I'm finding the limit as h approaches 0. But right now, I can have any h open as that variable, but I'm finding the limit as x gets closer, or as h gets closer and closer to 0, as that distance gets closer and closer. Does that help a little bit? Now what's really cool, I'm getting lots of fine stares. What's really cool about this is the math works out. Go ahead and simplify that. Turn to your table group, simplify. Yes, you distribute the 6. Did you remember how when we were taking the limit of an indeterminate form, there was always a way to make it so it worked out? We got rid of whatever was hanging us up. So do you remember we could factor, we could use a conjugate, use a common denominator, and I'm like, hey y'all, these are designed to work out. You're like, really? I'm like, yeah. So are these. It just becomes tricky on what you're plugging in. So if you notice when I distribute my -6 and I distribute this -1, you saw this -1 here, right? I get my x's canceling out. I get my 7's canceling out. I end up with -6 h over h. So guess what? My limit as x approaches 0, or the slope of the tangent line, is equal to -6. So my answer here is going to be -6. That's the instantaneous rate of change. Okay, let's come do this quadratic. So it's asking you to find the derivative. Whenever you see that little prime, remember they're asking you to find the derivative. And we're going to be using this conversation every time. We're going to find that because we're going to find, do this one in purple so you can make sure you tell the difference. I want to find the limit as that difference between my x values gets smaller and smaller and smaller. I'm going to look at the output of my second input value minus my first, and the difference between those x values is always going to be h. We can still write x plus h minus x, but then it's always going to be x minus x. Katie's working on it. Are you with me? Yeah? She was like, you were staring at it so intently, I loved it. All right, ready? So now we go to put into our function, and I gotta be honest with you, for me, this is always the easiest. Are you okay with that? Sometimes I cheat. You okay with that? Right? So I'm on my way. So now, instead of putting x into the function, I'm putting x plus h. That's your new input, right? X plus h. So what we're going to do is we're going to say, okay, that's 5, and instead of x, it's x plus h squared minus, not minus x, it's minus what? First function, second function. I like to do my first function first, but he's last. You okay with that? Now you know what's going to happen. Like lots of cool algebra is going to make it so it completely cancels out. It just is going to take you a bit to get there. Let's start here. 5 times x plus h squared is x squared plus 2xh plus h squared, right? Yeah?
Yes.
I boiled it. X times x is x squared. X times h is xh twice. Do you want to see it bigger?
Yes.
Oh my god.
But it's
That's spring of algebra 1, Claude. Spring of algebra 1, ready? X plus h times x plus h. FOIL. First terms, outside terms, inside terms, last terms, x squared plus 2xh plus h squared times 5. Killing it. Shoot. Minus x minus h minus 5x squared plus x. I'm already peeking ahead. I was never good at waiting. I read the back of the books. I did the prize out of the bottom of the cereal. I peeked at Christmas presents. Guilty. And then I got caught. That shamed me. I felt like
the surprise.
well, I was surprised at the minute I saw it.
I know, but like in the morning.
Right? Yeah, but like you're surprised. Like I found out that what the sex was of all of my babies, which is not a big deal now, but it was a big deal 30 years ago. And they're like, "Don't you want to know?" I'm like, "I'll be surprised no matter what you tell me." Like, "Oh, I'm surprised." I'm surprised no matter what. I don't like to know. My husband will tell you it's because I'm a control freak. Whatever. You think I'm a control freak? Who said yes? You know what? Of course I'm a control freak. I stand up here by myself every day doing exactly whatever I want to do. I almost forgot my denominator. Twice. I think Maria's laughing at me. See, she came in late. She didn't know that I had a bad day. Crying. Real tears over here, Maria. So this is the same. All right, ready? Look, these are like always designed to work out, and they're so very fun. It's like I can't wait. Because those 5x squareds, I was afraid of the quadratic. Don't be. It's there. Okay, so here's what I end up with. 10xh plus 5h squared minus h. Well, that's a lot of h's. Oh my gosh, I'm so excited you just said that. Because look, this H and this H.
No, other H, the other one. Right.
Why can't I do them all?
That's a lot.
Oh, would you rather I've done this? Good Lord. Maria, come here, come here. 10xh plus 5h squared minus h, right? I'm going to take an h out, and that's going to give me 10x plus 5h minus 1.
Whoa.
You okay? Hey, here's the really cool part. Come back here. Wait, there's more. The whole part of this that was messy was when I put 0 in for h in my function. Oh, I got that indeterminate form. But by substituting my function values in and doing some absolutely wicked cool math, I was able to eliminate that possibility of giving me that indeterminate form 0 over 0 again. So the beauty of mathematics is when all this stuff works out. So that gives me 10x plus 5h minus 1. And you're like scratching your head. You're like, you can't factor it. It's not a quadratic. What do I do with it? Stop. It's a limit. Rule 1 of limits. Plug it in. 10x plus 5 times 0 minus 1. 10x minus 1. Hey, guess what that is? That's the equation of the slope of the tangent lines of a quadratic curve. So when you have a quadratic curve and you're curious about the slope of the tangent line, and you're like, what is it? Oh, at whatever x point you're talking about, that's the equation of the line. That's your answer.
Yeah.
So we're gonna do all that.
How crazy is that? Wait a minute, stop and think about what you just got. Your answer was the equation of a linear line. It's this tangent line. The derivative is the line tangent to the curve at that point. So you're like, what is my instantaneous rate of change? You're like, I don't know what x you're talking about. You're like, this one. Put it into that linear equation, and you'll find this point of tangency right here. Of course, our answer is a linear equation because our original equation was a quadratic. We started out with a curve. So you want the derivative of the tangent line. Right?
Oh my god, this is all a good fail.
Alright, ready? Do you think we get one more? We can get one more done before you start screaming at me for being seniors and walking out the door. Are you ready? Are you ready? Simon, is that a good or a bad thing? I love it when it goes fast, don't you? Hey, ready? Hey, I'm so excited to do this. What color do you want to see it in?
Pink, purple.
Hey,
Pink.
hey,
Right.
hey.
Oh my gosh, overwhelming for pink. Here we go. Hey, I want to find the.
This is not.
I want to find. Can you even see that?
Yes.
It's the limit. No, not x. H. Darn it. Now I know you're laughing at me. I think my feelings are hurt. Ooh, didn't I tell you I had a bad day?
Are you making your day better, Miss Fraser?
No. Maria's laughing.
We're so happy at the laughter brings
Hey, I have to write the whole rule. F of x plus h is my second point minus f of x all over h. I can't plug h in because I get, so that's okay. I'm going to substitute my function in. And I'm going to cheat and jump to the end. Because that's my original function, right? Okay, now I'm going to do the 1, and instead of writing x, what am I going to write? X plus h, Grace says, I love it. 2 times x plus h squared minus 7 times x plus h. I'm going to change this, plus 1, and that's minus. That's the downside of doing it backwards. You run out of room sometimes. Now, lucky for you, this is still here. Look, lucky for you, this is still here. Something tells me you're going to get a lot of practice with this one. 2 times x squared plus 2xh plus h squared minus, oh wait, I got to put a parenthesis. I'm going to distribute the 7, minus 7x minus 7h plus 1 minus 2x squared plus 7x minus 1. Can you even see it in pink? Now I'm going to distribute that 2. 2x squared plus 4xh's plus 2h squared. Taking a breather. Because now comes the rest. Minus 7x minus 7h plus 1 minus 2x squared plus x 7x minus 1 all over h. And here's the beautiful part. This is where we get to look for the stuff to cancel out. I'm so excited I can't even handle it. See ya, Sally. No, because this minus makes that negative. What do I cancel? I heard it.
7x.
See you, Sally.
1.
Yeah, the one.
I forgot to write
GCFH.
Yeah.
Are you gonna make me take it out slowly, or can I just cross it out?
All of that one.
Are you making fun of me? This H, I'll take an H out of here. I'll take an H out of there. And I'll take an H out of there. So I end up with 4x plus 2h. What's left? Minus 7. Are we good? The limit as h approaches 0, when I plug in the h, I'm going to get 4x minus 7. That is the equation of the tangent line with this curve. So here's what's fun. I wrote too big, so we ended up skipping that one. Do you feel denied?
No.
No.
So here's your homework. I want you to look at it and try it. Don't, hey, listen. You don't learn by watching me. You learn by doing, and then coming into class and asking questions. So if you're ever frustrated about the people who get something, you're like, darn it, how come you get that and I don't? Maybe the answer is they worked for it. You know what I mean? Hard work in, result out, every time. Does that sound okay? Okay,